All right, diving into some academic notes on quantum field theory today. This stuff can get pretty dense, but I have a feeling there are some really fascinating insights waiting for us in these pages.
Absolutely. Johann Astborg, the physicist who wrote these notes, really has a knack for illuminating the core principles of QFT.
Well, from my initial skim, I have to admit, I felt a bit lost in the sea of equations. So maybe we can start by grounding ourselves. What exactly is quantum field theory?
Yeah, you're right. It's not exactly a light reading. At its heart, QFT offers a framework for understanding the universe not just as a collection of particles, but as a dynamic interplay of fields. Think of it like a vast ocean where the water represents the fields.
Okay, I can picture that. So where do the particles fit into this ocean analogy?
The particles are like the waves, these localized excitations of the underlying field. They're not separate entities, but rather manifestations of the field itself.
Interesting. So the universe isn't just particles bouncing around, it's this constant dance of fields creating and annihilating particles.
Precisely. And what's remarkable is that these fields aren't just abstract concepts. They have measurable properties and interact with each other, giving rise to the forces we observe in nature.
Now, the notes mention something called the Hamiltonian. Is that related to how these fields behave?
It is. The Hamiltonian is like a conductor for this quantum orchestra. It describes the energy of a system and dictates how it evolves over time. In QFT, the Hamiltonian helps us understand how particles and fields interact and how they change over time.
So it's not just about describing what the fields are, but how they actually behave and influence each other.
Exactly. And to make things even more interesting, QFT views these particles as quantized excitations of fields. This means that particles can only exist at specific energy levels. Like a vibrating string fixed at both ends. It can only vibrate at specific frequencies, producing distinct notes.
So just like a guitar string can only produce certain notes depending on its vibration, particles can only exist at specific energy levels within the field.
Precisely. And this quantization is a fundamental aspect of QFT, leading to some pretty mind-bending implications.
Now, speaking of mind-bending, I noticed some familiar names in the notes. Dirac, Higgs. These sound like major players in the QFT world.
They are. Think of them as the architects of different types of fundamental fields, for instance. The Dirac field describes fermions, the particles that make up matter, like electrons and quarks. What's remarkable is that Dirac's equation predicted the existence of antimatter, a concept that seemed purely theoretical at the time.
So antimatter isn't just a science fiction trope, it's actually a consequence of the mathematics of QFT.
Exactly. Then we have the Klein-Gordon field, which describes bosons. These are the particles that mediate forces, like the photon for electromagnetism. Each of these fields plays a crucial role in shaping the fundamental forces of the universe.
And then there's the Higgs field, the one responsible for giving particles mass. Wasn't its existence only recently confirmed?
Yes. The discovery of the Higgs boson in 2012 was a landmark event, validating decades of theoretical work and confirming the existence of the Higgs field. This field permeates all of space and interacts with particles, giving them their unique masses. It's a pretty incredible concept.
It really is. So we've got these fields, these particles, but how do they all interact? The notes mention Feynman diagrams, which seem like a fun way to visualize these interactions.
Feynman diagrams are an incredibly useful tool in QFT. They're a visual language for representing the complex interactions between particles, kind of like a comic strip of particle collisions. Each line represents a particle, and the vertices, where the lines meet, represent interactions between them.
So instead of getting bogged down in equations, we can actually see how these particles are interacting with each other.
Exactly. And what's even more impressive is that these diagrams aren't just pretty pictures. They translate directly into mathematical expressions that allow us to calculate the probabilities of different interactions.
So it's like a visual code that unlocks the quantitative side of QFT.
Precisely. They bridge the gap between the abstract concepts of fields and particles and the concrete world of experimental predictions. They allow us to calculate things like the likelihood of certain particles being produced in a high-energy collision, which can then be tested in experiments like the Large Hadron Collider.
Now, this is where I start to get a bit apprehensive. The source material mentions infinities popping up in the calculations. That sounds a bit alarming.
I understand the concern. These infinities were a major puzzle for physicists early on. But QFT has developed a way to handle them, a technique called renormalization. It's not about making the infinities disappear. It's about reinterpreting them in a way that allows for meaningful physical predictions.
So it's a way of taming these mathematical beasts and extracting useful information from them.
Exactly. Renormalization was a major breakthrough, enabling QFT to make incredibly precise predictions that have been repeatedly confirmed by experiments. This ability to make accurate, testable predictions is what solidifies QFT's place as a cornerstone of modern physics.
It's remarkable how QFT, despite its complexity and initial challenges, has emerged as such a powerful tool for understanding the universe.
It's fascinating how QFT has this reputation for being incredibly abstract and complex, but it's also remarkably grounded in reality. It allows us to calculate with incredible precision how particles behave in the real world.
That's what I find so compelling about it. We've been talking about these Feynman diagrams, and I'm curious about how they go beyond visualization and actually translate into concrete calculations.
Well, let's take the example of two electrons scattering off each other. In the quantum world, this scattering involves the exchange of virtual photons. These are temporary carriers of the electromagnetic force.
So these virtual photons are like fleeting messengers, zipping between the electrons to mediate their interaction.
That's a good way to think about it. Now, a Feynman diagram for this interaction would have two lines representing the incoming electrons, a wavy line for the virtual photon exchange, and two lines for the outgoing electrons.
I can picture that. But how do we go from this visual representation to an actual number that tells us the probability of this scattering event happening?
That's where the Feynman rules come in. Each element of the diagram, the lines, the vertices where the lines connect, has a corresponding mathematical expression. By combining these expressions according to the diagram structure, we can calculate something called the scattering amplitude.
So it's like a visual equation where each symbol translates into a mathematical term.
Exactly. When you square this scattering amplitude, you get the probability of that particular interaction occurring. Asborg's notes delved into the specifics of these rules, but the key takeaway is that Feynman diagrams bridge the gap between the theoretical framework of QFT and the experimental realm of particle physics.
It's incredible how these diagrams provide a visual language that unlocks quantitative predictions. Now, this whole idea of virtual particles popping in and out of existence, it's definitely one of the more mind-bending aspects of QFT. It makes me wonder about the nature of reality itself.
It's a question that has puzzled physicists for decades. Virtual particles are a consequence of the inherent uncertainty of the quantum world. They exist within the limits allowed by Heisenberg's uncertainty principle, influencing interactions but often confined to very short distances and timescales.
So they're like fleeting glimpses into the quantum fuzziness, playing a role in the interactions, but not quite existing in the same way as the particles we can directly observe.
Precisely. Their effects are measurable. For example, they contribute to the Lamb shift in atomic spectra, but directly observing them is a whole different challenge.
They're part of the quantum dance, but they dance to a different beat. Now, the notes also mention something called the S-matrix. How does that fit into all of this?
The S-matrix,
Yeah.
or scattering matrix, is a central concept in QFT. It's like a map that connects the initial state of a system of particles to the final state after they've interacted.
So it encapsulates the entire history of the interaction, from the initial conditions to the final outcome.
Exactly. And the elements of the S-matrix are directly related to the scattering amplitudes we were just discussing. By understanding the S-matrix, we can predict the probabilities of various outcomes when particles collide.
It sounds like a powerful tool for decoding the language of particle interactions, but how do we actually calculate this S-matrix? It must be incredibly complex.
It can be quite involved. But physicists often use a technique called perturbation theory in this approach. You start with a simpler theory where particles don't interact, and then gradually add in the interactions as small perturbations.
So it's like building up the complexity layer by layer, starting with the basic foundation and adding more detail with each step.
That's a good analogy. Each layer corresponds to a higher order of interaction strength, representing more intricate interactions between the particles. And remarkably, even with just a few layers, we can often obtain surprisingly accurate predictions.
It's like constructing a high-resolution image of the quantum world, pixel by pixel. Now, you mentioned that the S-matrix tells us about the interaction as a whole. I'm curious, is there a way to focus specifically on the interaction itself, filtering out the parts where the particles just continue on their merry way?
You're thinking of the T-matrix, or transition matrix. It's essentially the part of the S-matrix that isolates the interaction, removing the components that represent the particles simply moving along without interacting.
So it's like extracting the essence of the interaction, the core moment where something interesting happens.
Precisely. The T-matrix is often the most interesting part for particle physicists
Hmm.
because it reveals the dynamics of how particles transform and interact with each other.
It's like focusing on the key plot points in a complex story, the moments that drive the narrative forward. Now, you mentioned perturbation theory earlier. I'd love to hear a bit more about how it works in practice.
Perturbation theory is a powerful mathematical tool, but it's based on a surprisingly simple idea. We start with a free theory, a simplified model where particles don't interact. Then we introduce the interactions as small disturbances, or perturbations, to this free theory.
So it's like starting with a calm, still pond, and then gently dropping pebbles into it, creating ripples that represent the interactions.
That's a great visual. And by carefully analyzing how these ripples propagate and interact, we can approximate the behavior of the full interacting theory.
It sounds like a delicate balancing act, carefully introducing these perturbations without disrupting the underlying structure of the free theory.
It is. And the more layers of perturbation we add, the more accurate our approximation becomes. But even with just a few layers, we can often capture the essential features of the interaction.
It's like sketching a portrait, starting with broad strokes and gradually adding finer details until a recognizable image emerges. But I imagine there are limits to how far we can push this perturbative approach.
You're absolutely right. Perturbation theory works best when the interactions are relatively weak. If the interactions become too strong, the perturbations can overwhelm the free theory, and the approximation breaks down.
So it's like a magnifying glass that works well at certain magnifications, but becomes blurry and distorted if we zoom in too close.
That's a good way to put it. And studying strongly interacting systems is an ongoing challenge in QFT, requiring more sophisticated techniques beyond perturbation theory.
It seems like every layer we peel back in the quantum world reveals another layer of complexity. Now, there's a concept in the source material that caught my eye, the generating functional. It sounds intriguing, but also a bit intimidating.
The generating functional is a remarkably powerful mathematical object. Think of it as a master blueprint that contains all the information about a quantum field theory. It's like a compressed code that holds the instructions for generating all the Green's functions, which describe how particles propagate and interact.
It sounds like a mathematical seed that contains the potential for the entire theory to unfold.
That's a great way to think about it. And the beauty of the generating functional is that it provides a concise and elegant way to express the theory's dynamics. It's like a single equation that captures the essence of an entire symphony of particles and fields.
It's remarkable how such a compact mathematical object can hold so much information. But how do we actually use this generating functional? Is it purely theoretical, or does it have practical applications?
It has very real practical applications.
Hmm.
By manipulating the generating functional, we can derive all sorts of useful information about the theory. We can extract the Feynman rules, calculate the S-matrix elements, and even derive the equations of motion for the fields.
So it's like a multi-tool that we can use to explore different aspects of the quantum world.
Exactly. And the generating functional plays a key role in many advanced techniques in QFT, like path integral methods, which offer a different perspective on the quantum world.
Path integral methods. That sounds like a whole new rabbit hole to explore. But before we jump down that one, I want to circle back to a concept we touched on earlier, renormalization. It still feels a bit like a magic trick to me, making those pesky infinities disappear.
Renormalization is definitely a subtle concept, and it's not about making the infinities vanish. It's about reinterpreting them in a physically meaningful way.
So instead of trying to eliminate them, we find a way to incorporate them into the theory's framework.
Precisely. Renormalization involves absorbing those infinities into redefinitions of the theory's parameters, like masses and coupling constants. This is done in a very careful and systematic way, preserving the physical meaning of the theory while taming those infinities.
It sounds like a delicate balancing act, carefully adjusting the parameters without disrupting the overall consistency of the theory.
Exactly. And what's amazing is that this process of renormalization leads to incredibly accurate predictions. Validating QFT is a powerful tool for understanding the real world.
So it's not just a mathematical trick. It's a way of bridging the gap between the theoretical infinities and the finite measurable quantities we observe in experiments.
Precisely. And renormalization also reveals something profound about the nature of QFT. The parameters of a theory, like the mass of an electron, are not fixed constants, but can actually change with the energy scale at which we're observing them.
So it's like the universe is wearing different masks depending on the energy level at which we're looking at it.
That's a great way to think about it. This energy dependence of the parameters is a key prediction of QFT, confirmed by numerous experiments.
It's like the universe is constantly adjusting its wardrobe. and we're trying to figure out the fashion rules. Now, I remember reading about something called the renormalization group, which sounds like it might be related to this energy dependence.
It is. The Renormalization Group,
Mm.
or RG, is a powerful framework for understanding how the parameters of a theory evolve with changes in the energy scale. It's like a mathematical zoom lens that allows us to see how interactions transform as we adjust the energy level.
So it's a tool for tracking how the universe's wardrobe changes as we zoom in or out on the energy scale.
Exactly. And the RGA has been instrumental in understanding phenomena like asymptotic freedom, where the strong force actually gets weaker at higher energies. It's a counterintuitive concept, but it's been experimentally confirmed and has deepened our understanding of how quarks interact.
It's like the universe plays by different rules depending on the energy level, and the renormalization group helps us decipher those rules.
Precisely. The RG has been a key tool in understanding the evolution of the universe from the very high energies of the early universe to the lower energies of the present day.
It's fascinating how this concept of renormalization, which started as a way to handle infinities, has opened up a whole new way of understanding the energy dependence of interactions. It's like we've discovered a secret language that the universe uses to communicate its dynamics across different energy scales. It's amazing how we've gone from wrestling with those unsettling infinities to uncovering this hidden language of energy scales. It really highlights how QFT isn't just a static picture of the universe. It's a framework for understanding its dynamic evolution.
And speaking of dynamic evolution, there's another key concept woven throughout QFT that we haven't explored in depth yet. Symmetry.
Symmetry. I know it's often associated with beauty and balance, but how does it manifest in the world of quantum fields and particles?
Symmetry in the context of physics means that a system remains unchanged under certain transformations. Think of a perfect sphere.
Yeah.
No matter how you rotate it, it looks the same.
Right. So the sphere is symmetrical with respect to rotation, but how does this apply to the often chaotic world of quantum fields?
Well, in QFT, we encounter various types of symmetries, each with profound implications. One of the most fundamental is Lorentz symmetry, a consequence of Einstein's theory of special relativity.
Ah, Einstein. That definitely rings a bell. Does this Lorentz symmetry have something to do with the idea that the laws of physics are the same for all observers, regardless of their relative motion?
Exactly. It dictates that the laws of physics are invariant under changes in velocity. This has profound implications for QFT as it constrains the possible structures of the fields and the types of particles that can exist.
So Lorentz symmetry acts as a sort of cosmic rulebook, setting the boundaries for how particles and fields can behave.
Precisely. It ensures that the fundamental laws of physics hold true, regardless of how we're moving through the universe.
Right.
But there's another type of symmetry that plays a critical role in QFT, gauge symmetry.
Gauge symmetry. Now that rings a bell too. Didn't we touch upon that when we discussed the standard model of particle physics?
Yes. Gauge symmetries are intimately connected to the fundamental forces of nature. The standard model, which describes all known particles and forces, is built upon a combination of gauge symmetries, SU3 for the strong force, and SU2, XU1 for the electroweak force.
So these gauge symmetries are like the underlying blueprints for how forces work in the quantum world.
That's a great way to put it. Each gauge symmetry determines the properties of the force-carrying particles. For example, the U1 gauge symmetry dictates the properties of the photon, the particle that mediates the electromagnetic force.
It's incredible how these abstract mathematical symmetries have such concrete consequences for how the universe operates. But you mentioned something earlier about symmetry breaking, and I'm curious about what happens when these symmetries are disrupted.
Symmetry breaking is a fascinating phenomenon. It occurs when a system that exhibits a certain symmetry at high energies transitions to a state of lower symmetry at lower energies.
So it's like a cosmic phase transition,
Mhm.
where the universe undergoes a fundamental shift in its organization.
Precisely. And one of the most remarkable examples of this is the Higgs mechanism, which we touched on earlier when discussing how particles acquire mass. Right, the Higgs field. It's all starting to connect. But how does this Higgs mechanism relate to symmetry breaking? At extremely high energies, like those found in the very early universe, the Higgs field exists in a symmetric state. However, as the universe expands and cools, the Higgs field undergoes a spontaneous symmetry breaking, settling into a new state where it acquires a non-zero value. So it's like the Higgs field, initially balanced and symmetrical, suddenly tips over into a less symmetrical configuration.
That's a great analogy. And this tipping over has profound consequences. It's this process that gives mass to the W and Z bosons, the carriers of the weak force. Meanwhile, the photon, which mediates the electromagnetic force, remains massless.
So symmetry breaking is like a sculptor, shaping the properties of the fundamental forces and the particles that carry them. It's fascinating how this concept, which seems purely mathematical, ends up determining something as tangible as a particle's mass. It really highlights the power of abstract concepts in physics. Now, earlier you mentioned path integral methods. Would you like to delve into that rabbit hole?
Absolutely. From what I gather, they offer a completely different way of looking at QFT.
They do. Path integral methods provide a formulation of QFT that emphasizes the quantum nature of fields even more explicitly. Instead of focusing on individual particle trajectories, we consider all possible paths a particle can take between 2 points.
So instead of a single, well-defined path, we're considering an infinite number of possibilities.
Exactly. Each path is assigned a weight based on its action, a quantity that encapsulates the system's dynamics. The probability amplitude for a particle to go from point A to point B is then obtained by integrating over all possible paths, taking into account their respective weights.
It sounds like a mind-boggling calculation. Taking into account every conceivable path a particle could take, what's the advantage of this approach?
Path integral methods offer several benefits. They provide a very elegant and intuitive way to formulate QFT, emphasizing the wave-like nature of particles and the inherent uncertainty of the quantum world. They are also extremely powerful for handling systems with many degrees of freedom and for studying non-perturbative phenomena, where traditional methods based on perturbation theory break down.
So they open up a whole new avenue for exploring the quantum realm, allowing us to tackle problems that were previously inaccessible.
Precisely. Path integral methods have led to significant advances in our understanding of QFT and continue to be a vital tool for theoretical physicists.
As we wrap up this deep dive into quantum field theory, I'm struck by a recurring theme, the interconnectedness of everything.
Yes, it's one of the most profound insights that emerges from QFT. Particles aren't isolated entities, they're excitations of these underlying fields that permeate all of space.
And these fields are constantly interacting, creating a web of interconnectedness that extends from the smallest subatomic particles to the largest structures in the universe.
It's a humbling and awe-inspiring perspective. It challenges our classical intuition and reveals a universe far more interconnected and dynamic than we might have imagined.
Indeed, and it leaves me with a sense of wonder, knowing that we're all part of this grand cosmic dance of quantum fields. So, dear listener, as you continue your own exploration of the universe, remember that you are not just an observer. You are an integral part of this intricate, ever-evolving quantum reality.